Well, hello and welcome to Doc Onco's Physics. My name is Keith Onco, and today we're going to continue looking at kinematics in one dimension, and specifically in the y dimension. In the problem that we're going to look at today, we have a water balloon and we're going to drop it from a height of 5 meters all the way to the ground. And the first thing that we'd like to know is how fast will it be going, how fast will it be moving, just before it hits the ground. And that's always what we want to know. We don't want to know how fast it's going to be going after it hits the ground, because obviously it's going to be stopped. But the important thing is knowing how fast is it going to be going just in that fraction of a second before it hits the ground. Okay, so let's draw a little picture here. So here, whoops, there we go. So here we have a little cliff. I'm going to change to black. So here's our water balloon up here, and the height is 5 meters from top to bottom. Okay, and as I've said, I will always take my initial position to be the 0 position. All right, so this is going to be y equals 0 here, and if that's y equals 0 here in the center, then down here, right, this must be at the y equals -5 position, because we're going down. Okay, so if I look at my variables, all right, my variable table over on the right hand side, x initial, so x initial in the y position is 0. X final in the y position then is going to be at -5 meters. Okay, so we know that much. All right, so how fast will it be going just before it hits the ground? So what do we want to know? Well, I'd like to know v final in the y direction. Okay, what else do we know? Well, this is in a y dimension problem. So what do we always have? We always have an acceleration due to gravity, and we're here at the center of the Earth. We're here at the surface of the Earth, so it's going to be -9.8 meters per second squared. And remember that anytime I'm dropping something, right, I'm holding it, in the instantaneous moment right after I let go, right, the acceleration has not grabbed onto that balloon yet and started moving it. Actually, the acceleration has grabbed onto it, it just hasn't started moving it yet. And so my initial velocity in the y direction is going to be 0 meters per second. All right, so I know that. Okay, so I know a bunch of things. I don't know time. All right, and actually part B asks us how long it's going to take for the balloon to hit the ground. So let's see what tools from our toolbox up here we can use. Well, what are we looking for? We're looking for the final velocity in the y direction. Well, equation 2 here has final velocity. All right, we know the initial velocity, we know the acceleration, but we don't know the time. All right, so that's a problem. Let's see, the third equation here has nothing to do with final velocity, so that's not going to help us. Let's look at the fourth equation. All right, final velocity, which is what we're looking for, initial velocity, which we have, all right, acceleration, which we have, and the displacement, which we have. All right, so we can use the fourth equation to figure out what the final velocity is going to be. All right, now before I use that equation, let's make sure we understand that I'm dropping the ball from the y equals 0 point, and that ball is going to travel downwards, and so it's going to have some final velocity in the y direction, and it's going to be traveling down in the negative y direction. So our final velocity is going to have to be negative. Okay, one of the problems that we have when using the fourth equation here is because the final velocity term is squared and the initial velocity term is squared, we can lose the sign. Okay, so we just have to be aware of that when we use that fourth equation, that we can lose the sign. So you got to be aware of the situation that you have and apply that sign later on if the situation warrants that. All right, so let's see. So v final squared equals v initial squared. Well, v initial is 0 squared plus 2 times a times x. Well, 2 times -9.8 meters per second squared times the change, change in position x. Well, x final is -5, x initial is 0, right? So x final minus x initial, 0. So what do we got? We have v final squared in the y direction, should put a y there, is equal to 2 times negative 9.8, which is negative 19.6 meters per second squared, times negative 5. All right? And when we multiply negative 19.6 times negative 5, we get a positive 98 meters squared per second squared, and I should have a meters in there, always include the units, is equal to V final in the y dimension squared. So now finally, to get V final in the y dimension, I'm going to take the square root of both sides, all right, and V final in the y direction turns out to be 14 meters per second. So when our water balloon hits the ground here, or just before it hits the ground, it will be traveling at 14 meters per second. Okay, so that's part A. Part B says, all right, and we're going to add this to our table here. Part B wants to know how long it's going to take for the water balloon to travel that 5 meters to the ground. Well, what equations have time in them? Well, the second equation does, and the third equation does. Well, we could use the third equation, x final we know, x initial we know, initial velocity we know, all right, and time we're looking for. We could get that one, but that one looks a lot more complicated. It certainly does to me. We could use the second equation, right? We know V final now, it's 14 meters per second. V initial we know, A we know, right? And so T we could figure out. So, forgot to put the negative sign in the 14 down there, and this should be negative. Remember what I said before, V final, I lost the sign, right? I lost the sign when I took the square root of VF squared there, but I know that because the velocity is traveling in the downward direction, I have to apply the negative sign. So I just put it there in my table, all right? So negative 14 meters per second, okay, is equal to my initial velocity, which is 0, plus A, which is negative 9.8 meters per second squared, times T. Okay, and now all I really need to do is divide each side by negative 9.8 meters per second squared, and I get T to be a value of about 1.42 seconds. So that's how much time it's going to take the water balloon to hit the ground. Okay, I hope that helps, and we'll see you next time.